Hello everyone. The title of this video is Using Newton's Law of Cooling. So in this video, I'm going to be doing examples that are taken directly from a free online textbook at openstax.org. I'm in their Algebra and Trigonometry text, section 6.7, called Exponential and Logarithmic Models. And I'm under the heading, Using Newton's Law of Cooling. The examples I do in this video will either be an example from the reading or one of the try it problems from the reading or one of the exercises from the end of the section that's related to this particular objective. Alright, so Newton's law of cooling. The model we're going to be using looks like this, and they have a little box down here, and I'm going to be writing this up for pretty much every problem that I work on. And you see how it starts off like the exponential growth and decay model. Some number a times e to the kt, right? Just like we used for exponential growth and decay. The only major difference is this constant being added afterwards. Right? So here's Newton's law of cooling. The temperature of an object, T, capital T, in surrounding air with temperature T sub S will behave according to the formula. Right? So T of T, capital T of little t, equals a times e to the kt plus t sub s, where little t, lowercase t represents time. Capital A represents the difference between the initial temperature of the object that is cooling, right, and its surroundings. And that's what TS represents. TS represents the temperature of the surroundings, right? The temperature of the room or a pool of water or whatever the object is in. And this T sub S, for our purposes, will remain constant. And K is also a constant, right? The continuous rate of cooling of the object. Right? And you'll see that K will end up, when we're cooling, K will end up being negative. If for some reason something was heating up, this also works for warming, K would be positive. But again, I will write out this model for every problem we do, and let's just get into it. All right. So the first example I want to do related to Newton's law of cooling is example 5 from the reading. All right. So we're going through here. So example 5. So a cheesecake. Right? So our object in this problem is a cheesecake. A cheesecake is taken out of the oven with an ideal internal temperature of 165 degrees, right? So this is the initial temperature of the cheesecake, 165 degrees, and is placed into a 35-degree refrigerator. So this 35 degrees Fahrenheit, this is the this is that TS, that T sub S, the temperature of the surroundings, right? Because that's what you're surrounding the cheesecake in, right? This refrigerator. After 10 minutes, right, so it looks like time is going to be in minutes, the cheesecake has cooled to 150 degrees Fahrenheit. If we must wait until the cheesecake has cooled to 70 degrees Fahrenheit before we eat it, how long will we have to wait? All right, so now that I've read through it, and here's the Newton's law of cooling model that we're going to use for all these problems. The function capital T of, the input is little t, the input is time, equals, and this a times e to the kt power plus capital T sub s. And then once again I'll write out what this means. The lowercase t is representing time here, and this is in minutes in this problem. Right, for this particular problem, it's in minutes. It might be in hours or years or days or whatever for other things. T sub s is the temperature of the surroundings. Right, S, or what they call the ambient temperature, but I'm not using that word too much. Right, so in this particular problem, the surroundings is the refrigerator, which was at 35 degrees Fahrenheit. So I'm going to use 35 for the TS. Then, A, remember this capital A, they also wrote out what this A meant. This is the initial difference. So initial meaning, when time is 0. Right? The initial difference between the temperature of the object and its surroundings. So in this particular example, the initial temperature of the cheesecake was 165 degrees, and then we take the difference between that, the initial temperature of the object, and the temperature of its surroundings, which is again the refrigerator, which was 35 degrees. So this initial difference, the value of this A in our problem for this example, is 165 minus 35, which would be 130. Right, this is what I'm going to use for the value of A. So I've got 35 for the value of TS. I've got 130 for the value of A. All right, now all I need is to find K. Right, to complete this model, to make it complete and be able to answer any question they have. To complete this model, we need to find capital A, which we know, that'll fill that in, that TS, which we also know, the temperature of the surroundings, NK, right, and that rate of cooling, which is this in the exponent here. Now the A and the TS I know. To find K, I need some other information. Right, now they told us the following, that after 10 minutes, after 10 minutes in the refrigerator, in those surroundings, the temperature of the cheesecake was 150 degrees. Right, temperature of the object, temperature of the cheesecake is 150 degrees Fahrenheit. Right? So this means when T equals 10, capital T of 10, right, that'll be the left side of the model, capital T, the output, is 150. So I'm going to use this here, this information, this pair of numbers, 10 for little t and 150 for capital T. I'm going to use that, and 130 for A and 35 for TS. I'm going to use that to find K. So we have 150 on the left, that's the temperature after 10 minutes, equals, A was that initial difference between the temperature of the object and its surroundings, that's 130, times E to the K times T, so E to the 10K power, right, E to the 10K, K times 10, plus 35, right, the temperature of the refrigerator, the temperature of the surroundings. And I solve this for K. And you should know how to solve such a thing. Get this base in power alone. So I subtract 35. All right, 150 minus 35 would be 115 equals 130 times e to the 10k. Then we divide by 130. So e to the 10k power equals 115 divided by 130. This will reduce, though. Both of these are multiples of 5. This is 5 times 23, and this is 5 times 26. So this would reduce to 23/26. And then I change to the equivalent logarithmic form, right? So 10k must be equal to the log base e, or the natural log, of 23/26. And then to find k, right, I divide by 10, right? So k equals, the natural log of 23/26 divided by 10. All right, now, in a lot of the problems, if you've been reading through section 6-7, you'll probably notice that they take the value of k and round it to 5, sometimes 6 decimal places, and then put that in. So I'm going to do that here. I'm going to round this to 6 decimal places. Go to a calculator. I like using the Desmos.com, free online graphing calculator. Natural log of 23/26 divided by 10. And to 5, 6 decimal places, that'd be 0.012260. So 0.1226. Negative 0.01226. So negative 0.01226. Now you don't have to use this. You can use the exact value as well. All right, and I'll show you. So we'll pop all this stuff into the model. All right, so now this model looks like this. The temperature of the cheesecake, while it's in the fridge, after t minutes is equal to A, that was that initial difference, was 130, times E. Now you can use the exact value of k if you want. I write natural log of 23/26 divided by 10, then this times t, and then plus TS, that 35-degree temperature of the surroundings of the fridge. And then you saw me do this in the last video. Again, if you watched that last video from section 6-7 on modeling exponential growth and decay, this t divided by 10, I can put that inside using the power rule, make this 23/26 to the t over 10 power, and then use the inverse rule to undo the exponent and log, and make this 130 times, and then 23/26 to the t over 10 power, and then you have plus 35. So this is all fine. All right, so I'll use this or this, or, like I said, and again, you see this in the textbook. They're doing this a lot. You can just round the value of k to like 5, 6 decimal places and put that in. So I can use t of t equals 130 times e to the k, kt, negative 0.01226 times t power, and then plus 35. Every single one of these is exactly the same model. All right, and I'll show you. All right, I'll put up a graph of each of these. All right, I'll put up a graph of each of these functions on that Desmos site, and we'll see that they're all. The first two are exactly the same. The third one, because of the rounding, isn't exactly the same, but it's so close that it'll basically look the same. All right, so let me show you that here. So again, capital T of t equals 130 times e to the natural log of 23/26 divided by 10 times t power, and then plus 35, right? Okay, I gotta get rid of that subscript here. Just delete. Okay. And, zoom out a bit to be able to see this thing. There's the graph, right? So yeah, see the initial temperature of the cheesecake is 165, right? C0, 165. And that was told to us, right? The initial temperature of the cheesecake, 165. And then it should have the point, 10, 150, right? They said 10 minutes later, the temperature was 150, and you see that that point is on the graph, right there, 10, 150. So give it that. All right, and I'll put in the other ones just to show you it's the exact same stuff. 130 times 23 26ths raised to the t over 10 power plus 35. Plus 35. And you see that's right on top of the graph. It's the exact same picture. You can turn it off and on here. It's the exact same graph. Or you could use that rounded version of k. T of t equals 130 times e raised to the negative 0.01226 times t, and plus 35 after. And you see it's not exactly the same, but it's basically the same. It doesn't have exactly the same values. They're a little bit off, but they're so close, they look exactly the same. Right? So again, either one of these models is totally fine to use for this cooling problem here. Now the question was, right, let me go back to the problem. What was the question? Oh yeah, so if we must wait till the cheesecake has cooled to 70 degrees Fahrenheit, how long will we have to wait? Right. So I put it in the fridge, it was 165 degrees. When is it going to be 70 degrees is the question. All right, so now I've got the models up here. All right. So when is the temperature T of t here, capital T, going to be equal to 70 degrees Fahrenheit? So I just set the capital T to 70 and solve for T. All right. So it really doesn't matter which model you use. I'm going to go to the model here, the one without the e's and the logs. I personally like those. So using this second model, you can use the third one, the first one, it doesn't matter. I got 70 now on the left equals 130 times 23 26ths to the t divided by 10 power, and then plus 35. And then we solve this, it's an exponential equation. You should know how to solve, exponential equations like this by now. Get this alone, this base and power alone. So I subtract 35, that gives me 35 on the left equals 130 times, 23 26ths to the t divided by 10 power on the right. Divide by 130. Now 35 is 5 times 7. 130 is 5 times 26, so this would reduce to 7 26ths. 35 divided by 130 would be 7 26ths equals 23 26ths to the t divided by 10 power. And then if I change this to logarithmic form and then use the change of base rule, maybe put it in natural logs, we have t divided by 10 would be equal to the natural log of 7 26ths divided by the natural log of 23 26ths, and then I would just simply multiply by 10 to get t alone. And so here's how long it would take, how long we'd have to wait to be able to eat this cheesecake. It would be 10 times the natural log of 7 26ths in the numerator, and divided by the natural log of 23 26ths in the denominator. And I will enter this, and we can round to the nearest minute maybe. So let's do it here on the fourth line. 10 times the natural log of 7 26ths, divided by the natural log of 23 26ths. So about 107 minutes. So like an hour 47 minutes. Right. So there's about how long you'd have to wait. An hour, 47 minutes, under 2 hours, to then take the cheesecake out of the fridge and eat it for it to be cool enough. They could have also seen this with the graph. If I just put in y equals 70, right, and see where does it meet my graph, right, the graph of the cooling curve, it meets here at 107.03, right? So it would take 107.03, a little over 107 minutes to cool to 70 degrees. You can do that as well. Wonderful. All right. So the next example I have using Newton's law of cooling is the try it problem from the text, try it problem number 4. So let's look at that. That's the very next thing. So a pitcher of water at 40 degrees Fahrenheit is placed into a 70 degree room. So this will be warming. Now, I mentioned earlier that this could be a law of cooling or warming. And if it's warming, the value of K will be positive. Right? We saw in the last example when we were cooling, the value of K was negative. So the pitcher of water is the object. Right? Starts off at 40 degrees Fahrenheit and is placed into a 70 degree room. Right? 1 hour later, the temperature has risen to 45 degrees. Alright, so how long will it take for the temperature to rise to 60 degrees? Well, actually, the value of K might still be negative here, because if I use that initial difference, it'll be negative. Alright, so we'll see. But I'm still using the same model. Alright, still using the same model. T of T, right, the temperature of this pitcher of water. Alright, so yeah, K might still be negative here, now that I think about with the whole difference between the object and the temperature of surroundings. That difference is decreasing. It might be. We'll see. I think it's been a while. I think it's positive, actually. But we'll see. Sorry about the confusion. Let's just do the model. Let's just see what happens. So the temperature of the pitcher of water after T hours, time is given in hours here, is again some value A times E to the KT power plus, the temperature of the surroundings, TS, using the same model every single time. So TS this time, right, this is the temperature of the room, right? That's not changing. This is the surroundings, the thing that you put the pitcher of water into, and that is a 70 degree room, right? 70 degrees Fahrenheit. The value of A, right, it's the initial temperature of the pitcher of water, so 40 degrees. Right, this is the initial temperature, initial temp of the pitcher, right, of our object. And the difference between that and the temperature of the surroundings. Right, there's that room temperature again. So yeah, this ends up being negative. 40 minus 70 is negative 30. Right, so I'm going to use that for A. And then that's it. And then we should be able to find K using some piece of information. All right, so just using these two right now, we have the temperature of the pitcher at time t equals negative 30, the value of A, that initial difference between the temperature of the pitcher and the surroundings, times e to the kt plus 70, the temperature of the room. So yeah, so the value of K will end up being negative again because we're talking about the difference. Well, actually, it might be positive. I keep messing myself up with this. The initial difference is negative 30, and that difference should be shrinking. And going from negative 30 to near 0 is actually an increase. So I think, yeah, so I do think the value of k will be positive here. But we'll find that out in a second. They said 1 hour later, the temperature had risen. The temperature of the pitcher had risen to 45 degrees. So the temperature of the pitcher 1 hour later, right, so little t is 1, is 45 degrees. So I'm going to use that, set up an equation that we can solve for k. So I'd have 45 on the left side, right? 45 for t of t here, equals negative 30 times e to the 1k, right? T is 1 hour. So this becomes 1 times k. And plus 70. And then I solve this for k. So first I'd subtract 70. 45 minus 70 is negative 25. Equals negative 30 times e to the k. And then dividing by negative 30. 25 thirtieths is 5 sixths. So we have e to the k equals, and that'd be positive 5 sixths. Alright, so k ends up being negative still, because the natural log of 5 sixths will be negative. K is the natural log of 5 sixths. Okay, and if you want, we can round this to the 5/6 decimal places. Let's go back to the calculator. Let's get rid of all this junk. So let me punch in the natural log of 5 sixths. So negative, 0.182322 if I'm rounding to 6 decimal places. Right. So approximately negative 0.182322, right? So we can use that if we want, or keep it as the natural log of 5 sixths. Either way is fine. Alright, so I pop this into the model, and again, I'll write out the different versions of the model that you could use. So we could have T of T, right, the temperature of the pitcher, is negative 30 times e to the natural log of 5 sixths times t power, and then plus 70. Or put the approximate version in, negative 30 times e to the negative 0.12, or sorry, 182322 t plus 70. You can use that version as well. Or, going back to the exact version, I can put this t in as the power on 5 sixths and then undo the log. We have t of t with the inverse property equals negative 30 times and then 5 sixths to the t, and then plus 70. All right. And again, I personally prefer that third model without the e's or logs, but again, you decide which one you want. All right, now the question was, when will it be 60 degrees, right? How long will it take for the temperature of the pitcher to rise to 60 degrees? So when is the temperature of the pitcher, right, capital T, here equal to 60? So I just replace T with 60, capital T with 60, that's the left side here, equals, and then we'll have an equation that will solve for little t, right, we'll solve for time. So equals negative 30 times, 5 sixths to the t plus 70, and then subtract 70, you got negative 10, divide by negative 30, that's 1/3, positive 1/3 equals 5 sixths to the t. So t would be the natural log of 1/3 divided by the natural log of 5 sixths. And again, I'm just going to round this to the nearest, I'll do the nearest tenth of an hour. whatever. Let's just take a look at what this value is. So back here, I'll just go back to before this because it's just natural log of 1/3 divided by the natural log of 5/6. Ah, come on. Alright, let's just get rid of this then and punch it in again. Alright, so a little over 6 hours, 6.03 hours it would take. And this is, remember, this is time, and time was given in hours here. So it would take around 6 hours for this pitcher of water to go from 40 degrees up to 60 degrees, while it's sitting in this 70-degree room. Okay. But yeah, so it looks like no matter how we slice it, the value of k is negative for this model. Wonderful. All right, so I apologize for the thing I said earlier about it being positive sometimes. Just pay attention. All right. Okay. So again, using this same model, let's move on to the next examples. Now the next one I want to do is exercises 40, 41, and 42 from the book. And the reason I have these lumped together is because they're all related to the same situation. So back in the text, scrolling down to the bottom where the exercises are, going to 40, 41, and 42. Here we go. So for the following exercises, use this scenario. A pot of warm soup with an internal temperature of 100 degrees Fahrenheit was taken off the stove to cool in a 69-degree room. So that's the TS, right? 69 degrees is the temperature of the surroundings. And then the value of A would be 31, right? 100 minus 69, the initial temperature of the soup, minus the temperature of the surroundings. And then after 15 minutes, so time is in minutes here, the temperature of the soup was 95 degrees, right? So model the situation first, right? We got to find the A, TS, and K. So again, I'll write this every single time. The model we're using for this law of, now this would be cooling this time, it's not warming. The value of, T of T equals some number A times E to the KT plus some TS, where here TS is the temperature of the room, 69 degrees Fahrenheit. The value of this A, remember A, this A is the initial difference between the temperature of the object, so the temperature of the soup initially minus the room temperature, the temperature of the surroundings, which again is 31. So this is going to be 31 times E to the KT plus 69. And now I just need to find K using that bit of information they gave us, right? They said that T of 15, right? This is lowercase t, T equals 15 minutes, right? Time is in minutes here now. They said the temperature of this soup after 15 minutes was 95 degrees. So I'm going to use that, to solve for K, and then we'll have a complete model. So on the left side, I'm putting 95, right, the temperature of the soup, equals 31 times E to the KT, T is 15, so 15K, plus 69, and then we solve for K. So first I'll subtract 69, we get 16. No, that would be 26. 26, I'm sorry. It's 80 and 15, 95. So subtract 69, you got 26 over here equals 31 times E to the 15K. Divide by 31, we have E to the 15K equals 26 31sts. And then solving for K, we change this to natural log form and then divide by 15. This would be the natural log of 26 31sts divided by 15, which if you want, we can round to 5 or 6 decimal places. So here the natural log of 26/31 divided by 15. So negative 0.011726. Negative 0.011726. Right? So you can use that if you want in the model, or the exact value. It doesn't matter. Alright, so this time again I'll write up the versions of the model you can write once again. So we have T of t equals, I'll use the one with the rounded version first this time, why not, 31 times e to the negative 0.011726t, and plus 69, or T of t equals 31 times, now if I put if I put this natural log one in for k, you would put t over 15 as the power and then undo the log. So this would be 26/31 raised to the t over 15 power, and then again plus 69. Alright, so there's the models I'm using. Right, I'll use the second one, you can use the first one, it doesn't matter, they're pretty much the same thing. So that's the answer to number 40, right? Use Newton's law of cooling to write a formula that models this situation. Then for 41, to the nearest minute, how long will it take the soup to cool to 80 degrees Fahrenheit? So now, when is this happening? Right? When is T of t going to be equal to 80 degrees Fahrenheit? So I replace, capital T with 80. So on the left side I have 80 equals 31 times 26/31 to the t divided by 15 power plus 69. And then I subtract 69. That'll give me 11 over here, divide by 31. You have 11/31 equals 26/31 to the t over 15. And then I've done one of these already, take natural logs, then multiply by 15, right? This would end up being 15 times the natural log of 11/31 divided by the natural log of 26/31. Or just the natural log of 11/31 divided by k. Right, whatever that k was. Right. And they ask us to round this to the nearest minute. Right, so back on the calculator. So you know what, I'm just going to call this k. Right, this was the value of k, as k equals. And then the next one, I'm just doing natural log of 11/31 divided by k. So 88 minutes, if you're rounding to the nearest minute. So an hour and 28 minutes, a little less than an hour and a half. You'd have to wait for the soup to cool to 80 degrees. So about 88 minutes. Okay, cool. Then there was number 42. To the nearest degree, what will the temperature be after 2.5 hours? Now remember, they gave us time in minutes. So 2.5 hours I have to convert to minutes and then plug it in. Right. So same model, 2.5 hours. If that's the time, remember this is 2 hours is 120 minutes, half hour is 30 minutes, 120 plus 30, that's 150 minutes. Right, so that's going to be the value of t. So 2.5 hours, I'm finding the temperature of the soup after 150 minutes, t of 150. Alright, so I'm just plugging this in 31 times and then 26/31 to the 10th power. Alright, because 150 divided by 15 would be 10. And then plus 69, and then we're asked to round this to the nearest degree, right? The nearest whole degree. So back in the calculator, just clearing all this. 31 times 26/31 to the 10th power plus 69, right? So 74 degrees. To the nearest degree, that would be rounded to 74 degrees Fahrenheit. Alright, so after 2.5 hours in this 69 degree temperature room, the soup is still at 74 degrees. Alright. And again, same, next example I'm going to do, same model. I'm doing this same model for all of these cooling and warming problems where you take an object, put it into some surroundings, and wait for it to cool or heat up. So the last I'm going to do is exercises 43, 44, and 45 from the same set of exercises. So it's pretty similar. Pretty similar. So, a turkey is taken out of the oven, just like the soup. Just like the cheesecake. And the initial temperature of the turkey is 165. This is basically like the cheesecake one. And it's allowed to cool in a 75 degree Fahrenheit room, though. It's not put into the fridge, it's put into just a room that's 75 degrees. So the value of that TS is 75, and the value of that A is 165 minus 75, that'd be 90. Right? The initial difference between the object of the temperature and the object of the temperature of the surroundings is 90 degrees. And then after half an hour, now I know they gave us hours here, but we could do minutes, because I noticed later they're asking us for, to the nearest minute. So just to make that problem a little easier, I'm going to have my time be in minutes. Now you can have time be in hours as well. We'll just do half for an hour, but I'm going to use 30 minutes instead. The internal temperature of the turkey is 145 degrees. Right, so first I'm going to write a model. So again, the cooling model, same thing every time. T of t equals a times e to the kt power plus t sub s. But for this one, TS, the temperature of the surroundings, is 75 degrees Fahrenheit. And this also works for Celsius if everything's in Celsius or Kelvin. Just pay attention. The value of A, though, right, the initial temperature of the turkey was 165. And then you subtract, the temperature of the surroundings, take that initial difference. So again, I said that was 90, right? So using these two, we have T of t, the temperature of the turkey after T, and I'm going to use minutes. I'm going to go minutes for time, is 90 times e to the kt plus 75. Right. Now we just need to find k, and that's, they said half an hour later. That's half an hour, 30 minutes. They said after half an hour, the temperature of the turkey was 145. Right, so I'm going to use this to find k. So I got 145 on the left equals 90 times e to the 30k. Then plus 75. Just replacing t with 30. Right, 30 minutes if I'm doing time in minutes. Alright, then we subtract 75, which will be 70 over here, equals 90 times e to the 30k. Divide by 90, I've got 7/9 equals e to the 30k. And then the value of k, I'm hoping you see, would be the natural log of 7/9 divided by 30. And we'll and round this to 5 or 6 decimal places. So back on my calculator, this time I'll actually write k equals, we'll call it the value of k, natural log of 7/9 then divided by 30. Right, so negative 0.008377. So negative 0.008377. Right. So you can use that if you wish. You can use that if you wish. All right, so the full model then, right, the answer to number 43, exercise 43 then is this. T of t equals 90, that initial difference, times e to the k, negative 0.008377 times t power, plus 75, or, if you don't like using the rounded stuff, like I don't, t of t equals 90 times, and if I put this in for k, t over 30 would go and be the power of 7/9, and then I'd undo the log with the inverse property, so we'd have 7/9 to the t over 30 power, and then plus 75. Right, so either one of these is fine as the model, the answer to number 43. All right, then exercise 44. To the nearest degree, what will the temperature of this turkey be, after 50 minutes? So again, I'm glad I used time in minutes. So now I can just plug in 50. I don't have to convert this to hours. All right, so after 50 minutes, so what's t of 50? Well, that would be 90 times 7/9. Now 50 divided by 30 is 5/3, right? So the power on that would be 5/3, and then plus 75. And we're asked to round this to the nearest degree. So I'll punch this in. So we have 90 times 7/9 to the 5/3 power plus 75. So 134 degrees if I round to the nearest degree. All right, so it started off at 165 degrees, and 50 minutes later in this room, just to sitting out in the room, it's still at 134. All right, still at about 134 degrees. Okay, and it should be lower, right? If you ended up with a number higher than 165, then you did something wrong, right? Because it's a 165 degree turkey sitting in a 75 degree room. It should be cooling. All right, then the last part of this, number 45, right, and using the same model, so keeping the model up there. Exercise 45 is, to the nearest minute, how long will it take the turkey to cool to 110 degrees Fahrenheit? So you're solving this equation. When is T of t equal to 110 degrees Fahrenheit, right? So 110 for the output, 110 for capital T equals 90 times 7/9 to the t divided by 30 power plus 75, and then I solve for t, right? So get this base and power alone, then change to logarithmic form. So first I subtract 75, so that'd be 35 over here, right, equals 90 times 7/9 to the t over 30 power. Then dividing by 90, now these are both multiples of 5. This is 5 times 7, this is 5 times 18. So that would reduce to 7/18 equals 7/9 to the t over 30 power. And then I change to log form and solve for t. We'd end up with t equals 30 times the natural log of 7/18 divided by the natural log of 7/9, which is really just the natural log of 7/18 divided by k. right? Because K was the natural log of 79 divided by 30. If I divide by that, you'll flip it, right? So I just taken the natural log of 7/18 and dividing by K back in the calculator. So I already called K a certain value up here. So now I'm just taking the natural log of 7/18 and dividing it by K. So 112, 113 minutes if I'm rounding to the nearest minute. So it would take a little under 2 hours, right? 120 minutes is 2 hours. So it would take a little under 2 hours for the turkey to cool down to 110 degrees if it's sitting in this 75-degree room. All right, and that's all I've got. And you've seen I was doing the same thing every time here. Same model, same setup. What's the value of the TS, the temperature of the surroundings, the value of that capital A, which was the initial difference between the temperature of the object and the temperature of the surroundings. And then you used one bit of information, one pair of numbers that they gave you to find K. You set up your model, and then you use that model to answer any question they had after that. All right, and I'm hoping that watching me go through these 4 examples here helps you in some way when you're asked to use Newton's law of cooling or warming on your own. And thank you very much for watching.